Let's rock and roll with vector addition. How do we get from here to there? For instance, you're flying a plane at 150 meters per second at a bearing north 16 degrees east. You're flying into a wind of 22 meters per second coming out of the southeast. Say what? Coming in at west 27 degrees north. What is your resultant velocity? Let's take a look. North 16 degrees east. We start at north. We go 16 degrees this way. There's our vector. We've got a magnitude of 150. Write small in case you need this side of the triangle. Now, time for a new vector. You got to make a little baby coordinate axis where you are. This is a swept off course problem. There's wind, you're not doing anything about it. What happens next? You draw your vectors tip to tail. That's how you add vectors, tip to tail. They're tail to tail or tip to tip. If you've got two arrows banging against each other, that's not an addition problem. Check your math. We're doing an addition problem west. That's here. We go 27 degrees. It's about a third of the way up to here or so. And we've got another vector here. It's a much smaller vector. You don't have to draw things to scale, but if you want to be in the proper quadrant, it helps. There's our 22. And here, that little tiny angle here is 27. No, the 27 degrees is not the whole thing. If you want to know what this angle is, you can break this vector into components. Notice you're going mainly north. Here's your northern component of the first vector. And you're going some east. This is your x component. This is your y component. If you find that drawing to scale means it's so small you can't see anything, then make your picture bigger. It is possible to add these vectors using the log sines or the log cosines, but I don't recommend it. I recommend finding the components of this one. This one goes mainly west and a little bit north. The question is, does this one go so far west that you're really going here into the west, or are you still mainly going in the northeasterly direction? Let's use the component method of vectors and find out. Your resultant velocity is here. This is where you're going to be going. That's the vector sum. Break each vector into components. Write it in bracket form. Each one of these has a magnitude. Its magnitude is 150. Each one has a reference angle. We'll call that theta. This side is opposite. Sine is opposite over adjacent. That makes this one 150 sine theta, and this one 150 cosine theta. Please note that the theta we use in order for this formula to work has to be measured from the positive x-axis. This is measured from the north. We can't use it. This is measured from the west. We can't use it. Pause the video and convert all of these angles to proper math class angles ready for the formula. Press play to check your work. If you got 74 degrees, check it out, we should be in the first quadrant. You are good to go. If you got an angle in the second quadrant of 180 less 27 to get 153 degrees, then you are good to go. Now, break your vectors into components. When you write that little vector sign, it's a sign that there had better be brackets and commas for all of these. One comma with two spaces if you're 2D, add another comma in a third space if you're 3D. Each one is going to have a magnitude cosine theta. Each one is going to have a magnitude sine theta. Pause, do your math, express these vectors in component form. Before you start typing, make sure your mode is in degree mode. In the newer operating system, this is going to be found in a menu. Otherwise, you will need to type in this degree symbol, which is in the same menu with E and pi. I repeat, on the TI Inspire, you can't type in cosine 74. It has to be cosine 74 degrees to get this in decimal. However, if you're typing this in on an advanced calculator, you don't need to type in 4 steps if you don't want to. You could do the whole problem at once and be done. Type in 150, vector. Vector in your case is curly brackets, go figure. Cosine, 74. I changed my mode, but I'm okay. You didn't, so you're going to need 74 degrees. There's your first decimal. Sine 74. There's your second decimal. Don't forget to close your parentheses. Close your vector. Plus, here's the second one, 22. Cosine, check the quadrant, 153 degrees. What did I forget? What did I forget? Oh, that's right. I'm not just doing one, I'm doing two. Cosine. Vector. Cosine, that's better. 153 degrees. Close your parentheses. Put in your comma. Sine. 153 degrees. Close your parentheses. Close your vector. Proofread, proofread, proofread. Enter. Bam. Final answer. There is your resultant velocity. 22.7 in the x direction, 154 in the y direction. There's your resultant. Write it down. Check the sign. 21.7. That's positive. Check the sign. 154. That's positive. We are in the first quadrant. Our assumption was correct. Our picture was correct. Here we are going north and a little bit easterly, but not as much as we would have done before. Read the problem. If the problem says find the final velocity, this is it. You're done. That's the final velocity. Velocity is a vector. You can express it in Cartesian coordinates. You can express it in component form just as nicely as the other way. If the problem asks you to find the final speed and direction, that's different. Then you need the Pythagorean theorem. Here's your x component, here's your y component. Work your Pythagorean theorem, work your arctangent, plus pray to check your work. Ready? Got 155 meters per second of speed. You've got a little bit of a tailwind there, speeding you up. However, you're a little bit off course. You're 82 degrees instead of 74. You're going north 8 degrees east instead of north 16 degrees east. Stop, quadrant check. My calculator said 82. Is it really 82? Well, first quadrant, yeah, I'd say that's about 82. We're not in the second quadrant. We're not in the third quadrant. The alternate form of our final answer could be any one of these final forms, 155 meters per second, north 8 degrees east, or any of the congruent angles.